think we start now. Hey everyone, my name is Ulrika Karlsson. I'm a visiting professor here at the school. I'm teaching the Performative Design Studio, and some of my students, or all my students, are engaged in Bernard Cash workshop this week. I also have a practice called Server Stockholm. And I'm very honored to have been given the opportunity to introduce Bernard Cash today. Bernard Cash, you're an independent theorist and architect and industrial designer from Paris, where you also run the workshop-based practice Objectile. You're researching on the use of digital tools and computational techniques for architecture conception and production, and overlaps this with scholarly work on early architecture theory, particularly on the texts of Vitruvius. And recent books by Bernard Cash is the Projectiles, which is published by an AA Architecture Words publication that came out 2011. And then we have this very famous one from 1995 called Earth Moves, which was around the digital turn for many of the architectural schools around the world. The first time I met you, Bernard, was actually at the Architecture non-standard exhibition in Paris at the Centre Pompidou, where you, with Objectile, but also my practice, Servo, were invited to exhibit. But the name of the exhibition was specifically referring to your work and the theory on the non-standard and the idea of the Objectile. As you say in your text, Objectile, the name of Objectile was given by the philosopher, very famous philosopher, and your professor, Gilles Deleuze. 1988 in French and 1995 in English, to be correct, in his book, The Fold. To the research that you were conducting, as well as some others, where you were carrying out, looking into the possibilities of industrially produced non-standard objects, or how to work with repeatable variations on a theme. Objectile being a generic object defined by several parameters or associations, which only becomes a specific object when each parameter is assigned a value. The notion of the objectile has been very important for the continued development of architecture theory and practice engaged in digital design and fabrication. But today, your focus and title of the lecture is Dürer, Vitruvius, Plato, Instruments of Thought. And I guess that relates to what you have said in a recent text that will be published in the book that Helen Frishaw is just editing.
It's also in Projectiles. Yeah.
It's also in Projectiles, where you say that what is actually lacking today is long-term thinking, reason, and an engagement in history. Welcome.
So thank you very much, Ulrike. And I didn't know that my students in the workshop had such a teacher as you. So thank you. And so what I would like to do this evening is to try to demonstrate that parametric design and mechanics are not new in architecture. They are actually there from the very beginning of the written sources of our discipline. And to understand that, we have to come back to classics such as Euclid, Plato, and Vitruvius. My guess is that a renewed reading of those classics has the potential to bring contemporary architecture back into a historical tradition. So in order to demonstrate that, I will mainly rely on an intermediary character, Albrecht Dürer, the great artist of the German Renaissance, who lived at the turn of the 16th century in a period that is roughly somewhere between our times and antiquity. But instead of showing his wonderful paintings, I will mainly focus on his treatise of geometry, the Unterweisung der Messung, or the instructions for measurements that were written in 1525. So this treatise is a rather unique case in the history of mathematics because it is written by a non-mathematician for non-mathematicians. Dürer was a painter, first educated as a goldsmith, and he wrote his treatise for all kinds of craftsmen, among which carpenters, stonecutters, and architects. So this explains that this treatise is organized by figures and not by propositions. Dürer actually explains procedures rather than makes demonstration, although we will see that there is one very important exception. Actually, very often, rather than geometrical figures, what Dürer shows are mechanical instruments intended to draw curves. And those instruments take so much importance that sometimes the curves are not even represented. So this practical and mechanical turn explains that in order to read this treatise, we need a CAD/CAM software which enables us to establish parametric relations between elements in the figures, to model the mechanical instruments, to simulate their movements, in order to finally generate the trajectories that Dürer refrains from showing us. So doing, we have to bring mechanics into the field of fine arts. And this should be of no surprise to us, since if we come back to the main written sources of our discipline, the De Architectura of Vitruvius, we would already find such a thing. Indeed, the topic of the De Architectura is not at all restricted to the Greek temples, neither to the three classical orders, Doric, Ionic, and Corinthian. Vitruvius' second definition of architecture is that architecture consists in three parts: the construction of buildings, edificatio, the construction of solar clocks, gnomonica, and the construction of machines, machinatio. And indeed, if you look at the table of contents of the De Architectura, you can consider that the two first books constitute the introduction, and then from book 3 to book 7, you have the part dedicated to edificatio, the construction of buildings. Then you have a strange book, which is book 8 about hydrology, but then book 9 is dedicated to gnomonica, and book 10 to machinatio. And the number of books is only a rough indication of the content, since, for instance, book 10, the mechanical book, has as many pages as book 3 and 4 altogether, which are dedicated to the temples. And in addition, the first building mentioned as such in the De Architectura incarnates perfectly well this definition of architecture. So we have to look to this first building, which is the Tower of the Wind, built by Andronikos de Kieros in Athens in approximately -100. So obviously, this tower looks like a building. I guess on this aspect I will have no difficulty to convince you that this object falls under the category of edificatio. But what about gnomonica and machinatio? So let us look at one of the drawing made by James Stewart and Nicholas Revett of this tower, where you can see light lines here that were the lines of the 8 solar clocks that you had on each of the wall of this octagonal tower. So let us look at the tower here, and especially let us rebuild the diagram of the analemma of Vitruvius, which is described in book 9. So this diagram is fully parametric. First of all, there is one first parameter that is essential, which is the latitude of the place. So if I change the 38 degrees of Athens to Roma, you see that it's already slightly moving. But then this has to take into consideration the season. So let's move from February to June, and be aware that this is, of course, in 3D dimensions. And then, of course, the same diagram applies to each of the 8 planes of the tower. So we have to change the orientation of the walls in order to fully understand the capacity of variation of this diagram. Okay? So what is strange in the De Architectura, it is that Vitruvius explains quite well the analemma, but does not explain how the curves project on the building or on the solar clock. I think there is one possible explanation, which is that you have to take into account that in antiquity, most of the solar clocks were not projecting on planar surfaces. Actually, you have here a list of all the categories of solar clocks that we have left from antiquity. So there are conical, spherical, planar, and cylindrical. And you see that planar solar clocks are only 16% of the total. Most of the solar clocks were actually on curved surfaces like those ones. And actually, you also had multiple sundials, such as this one, who was precisely designed by Andronikos de Kyros. So the architect of the Tower of the Winds was actually an expert in mnemonica. Now, let's switch to machinatio. So nowadays, if you go to Athens, you see nothing within the building. There is nothing left of a huge mechanism that was inside and that has been reconstituted by American archaeologists 30 years ago. So in this mechanism, so I have to show you back the building on the picture, because what you see here, this cylindrical tower, was actually a tank, a water tank, from which the water was spilling down into a lower inner tank, and there a float was lifting a cable winded around an axis which had a big bronze disc rotate. So all the question is, what was this disc all about? In order to understand that, you have to remember what a stereographic projection is. So stereographic projection is based on a sphere. You take one point on the sphere, and then you take the diametrically opposed point, and you have a plane pass orthogonally to the diameter. And what is very strange in this particular type of projection is that any circle that you draw on the sphere, even slanting, is projecting on circles onto the plane and not in ellipses. And not only this type of projection conserves the circles, but it also conserves the angles between the different circles on the sphere. So I hope you can distinguish here that in this particular, with those particular circles, the tangent makes an angle of 138,78 degree. And you see the same angle here in the projection. And if I move the point, you see that it modifies the circles, but also it keeps invariant the angle of intersection. if you think that this is old-fashioned geometry, just remember that Henri Poincaré took the stereographic projections as a model for the unfortunately called non-Euclidean geometry. So there is nothing, in old geometry that is totally outdated, and most of the time, modern and contemporary mathematicians come back to it in order to take example for new discoveries. So let's come back from contemporary mathematics to mechanical clocks in antiquity, and let's consider the main problem of the engineer at the time. The problem was that hours had a variable duration according to the seasons. And thanks God, Vitruvius was not living in Sweden. He was only in Rome. So in Rome, the duration of the day varies between summer and winter in such a way that the winter hours are only 3/4 of an hour. And if you divide the duration of the day by 12, and if you divide the summer duration of the day, you get 1 hour and 15 minutes. But still, how do you measure variable units with a constant speed mechanism? So the answer is that you use a network of conversion curves. So in front of the big Bonds disk that I showed you before, each time I'm manipulating the software here, that's real-time demo, so sometimes it takes some time. So in front of the disk, what you see here in red are metal wires that establish the connection, the conversion between the variable hours of the time and the constant rotation of the disk. So the blue one here is the horizon, well, the stereographic projection of the horizon. And as you can see here, there are 12 little arcs that are the day hours. So let's have it rotate just as the water tank would have done. And here you see the sun that had to be displaced each day in a little hole that was made in the disk in order to have a different height upon the horizon according to the season. So as you can see, that was already a complex mechanism. And indeed, I think that the first Vitruvian building is not a classical temple, but it incarnates quite well the three parts of architecture, since it was a building, edificatio. It bears at least 8 planar sundials, gnomonica, and above all, it was a machine, machinatio. To be sure, it was not a machine for living, a machine à habiter, as would have said Le Corbusier much later, but it was a machine that produced information, so it was what we would call today a computer, from the Latin verb computare, to calculate. And I think Dürer inscribes himself within this antique tradition of both variation, parametric and mechanical. In order to understand that, you must realize that the main topic of his geometry treatise are instruments, be they drawing instruments that bear the name of 3 animals, the snail, die Schneck, the spider, die Spinne, or the snake, die Schlange, but they were also calculating instruments. So, for instance, to calculate the conchoid of Nicomedes, or even an instrument that Dürer attributes to Plato. You know, this idealist philosopher who is supposed to say that geometry should remain a kind of idealist object and not incarnate into matter. So we have to question that. and start with the snail line, which is actually, the first one is a Yannickel volute taken from the De Architectura. So let's see how it looks. The screen is reduced because there is a projection, so. Okay, there it is. So what you have to understand is that what Vitruvius describes in a very obscure chapter, because unfortunately it relates to a drawing that has disappeared as all of the drawings of the De Architectura, as Mr. Mario Carpo could explain you quite well. So this chapter is actually about a very rudimentary instrument, since you had in the middle of the oculus of the volute 4 nails to which was attached a string, and the game was to have the string rotate around the 4 nails, and as you can see, each time the strings intercept a nail, it reduces its length, and this built up the spiral of the Yannickel volute, which is the first of the snail lines of Dürer. Actually, Dürer's one is based only on 2 nails, because he's actually probably following the text of Alberti. And this is the first variation upon the instruction of Vitruvius. The next snail line is actually, from Dürer, is actually the Archimedes spiral, which we could consider is the same type of instrument with not anymore 4 nails, not anymore 2 nails, but 1 single one. And actually, there was no mechanical instrument, neither at the time of Archimedes, nor at the time of Dürer, in order to draw this machine. Actually, the instrument will be invented a little bit later by Huygens, and this is the drawing that Huygens made into a manuscript of this machine. So, with no machine, I should say, with no mechanical instrument, Dürer has to invent what I would call a digital instrument, because he makes an association between a number of points that you can see equally distributed on this radius with a number of angles around this circle. So what he does, you take angle 1 here and you associate it with distance 1, then angle 2, distance 2, and so on, and then you build up this spiral of Archimedes. What is important to understand, it is that here, this digital instrument is used for a planar curve. And actually what is very interesting, it is to see that Dürer will be using the same device in order to describe a 3D curve. So actually, what is the ancestor of descriptive geometry actually has nothing to do with representation of space on the 2D plan of drawing, but has to do with establishing a correspondence between series of points or series of numbers that can be distances or angles. So what now you must understand, it is that just after the description of Archimedes' spiral, Dürer says, now I shall alter this previously made spiral once more. He says once more, or noch einmal verändern, because there was first the Vitruvius volute, which is actually a variant which comes from Alberti, and then Archimedes spiral, and now we are already in the third snail lines. So each time things are put into variations, and I think we can take for granted that there is a general principle into the Unterweisung der Messung, which is that nothing is affirmed or asserted in this text that is not susceptible to be put into variation into a further drawing. The whole principle about of the Unterweisung der Messung is the principle of variation. And here, for instance, rather than having an equal distribution of points according to along the radius, you have a varying distribution, because in this case, what is equally divided is not the line here, but the arc, and this project into unequal intervals onto this line. And as you can see on this diagram, immediately Dürer considered that rather than having a vertical line, you could also have a slanting line according to any angle. So where does this diagram comes from? For that we have to switch further into the treatise of geometry and go to this tower, which is at the beginning of the section dedicated to the alphabet. On this tower, you see words that are written with varying height letters. Okay? And this is done in such a way that the upper letters appear with the same apparent angle to an observer that is here as compared to those who are close to the ground. So this is because Dürer is now referring to the optics of antiquity, where the image of an object is not at all the intersection with the plane of representation, but is an apparent angle. So what is very interesting to see, it is that Dürer is actually the first German theoretician of perspective in Renaissance. So he knows quite well the perspectival techniques, but still he is alluding to the optics of antiquity. So here is one of the other drawing of Dürer, much less famous than this one, but it is the most interesting one because here you can see that the eye is a mechanical eye. It's just a nail in the wall. And here the two persons are working in team in order to repeat a procedure that enables to build each of the points to represent this musical instrument. So what is really important to understand it is that Dürer, just as Leonardo da Vinci, had actually both systems in mind. Already the Renaissance perspective, but still the optics of antiquity. And I think it's very important to see that history is not progressing at a regular pace. There are constantly superposition, well, survival of the past and anticipation of the future. And for instance, if we take Leonardo da Vinci and the representation of a series of columns from an observer that is located here, Leonardo da Vinci will never accept that the image be only a circle for the column in front and becomes an ellipsis. Well, I mean, not a column, not here, a sphere, becomes an ellipsis when it is on the side. If you take, for instance, another example of that, if you take the project of Juan Caramuel de Lobkowitz for St. Peter in Roma, this is a project of Bernini that has been built, but the one of Juan Caramuel would have been much more interesting with elliptic columns that actually correspond to equal apparent angle for an observer located in the center of the piazza. And here you see the series of varying sections of the columns. So similar principle of deformations could be also found in Vitruvius' De Architectura under the name of optical corrections. And I think that what is important is to understand that the general principle was to deform the deformations in order to restitute original proportions. And that's actually a key concept of the Plato's dialogue, the Sophist. So we are back in minus 365 approximately in history. So let's see now how this works with Dürer's mechanism. So here, and this is something we have done with the students in the workshop. So here you have, if I'm looking on the top, you recognize Dürer's diagram. And because we have now much more sophisticated digital tool, we can translate the digital instrument of Dürer onto a kinematic model that you see here. And I will have the diagram moving along a vertical stalk in order actually to simulate what Dürer is showing us here. Okay, and here you see how the correspondence between the series of points goes from the 2D representation of a planar curve into the 2D representation of a 3D object. Interestingly enough, this is used to create architectural objects. So this spiral, and here you recognize this device of the optical diagram. You see it used to have spiraling fluting along a vertical shaft, and here you see it used for a spiraling column that is actually much more complex than the one that Bernini will build for the baldacchino of St. Peter. So I have to show you what the student did into the workshop, and we'll see how we can use that in a project with varying columns. So here I have already a series of those columns, and I will create a new one for you. So I'm dragging here a family behind which there is the mechanism that I showed you before to generate the Dürer's spiral. I will locate here provisionally the column. I have to show you that I can control its height like this. Okay, so I accept the variation that I want. Now I will position it, so I have to show the positioning frame, and there I locate it here, and there we are. We can now modify the project the way we want. Okay, so there is, I think, a direct translation of Dürer's geometry into the method of CAD/CAM today. You know, really the first time I read it, I just saw already how this could be translated onto a parametric software. So, ironically, Dürer is showing the regular helix after the varying spiral of those columns because he's not interested into regular object. So now we have eaten the snail and we have to eat the spider. This is the drawing that Dürer provides us with. And as you can see, it is very rudimentary. So we have to look how the instrument looks like here. There it is. So let's simulate its movement. And here you see it. Of course, but as Dürer say in his text, everything can vary. And the first thing that can vary is a sense of rotation of the two arms that you see here. So let's modify the sense of rotation. There we are, and we get a circle. So we have made a complex instrument to simulate what the compass does. But what is the purpose of it? It is that this purpose is off-center relatively to the pivot, the main pivot of the basis. Okay? So we can do many, many different variations. So I can, for instance, here put 2, and interestingly enough, these instruments that works exactly like Ptolemaic astronomy is actually capable of simulating an ellipsis that will come much later in astronomy with Kepler. Or if we now put stronger variation like this, we get curves that are typical of the Baroque era that will arrive some 50 years after. Okay, so now the question is, why is Dürer calling this a spider? So the first answer could be taken from Vitruvius, who is naming one of the solar clock, the one from Apollonius, a spider. But to be sure, there is an analogy here between the position of the different arms, the different position of the two arms of the machines with the arms and the legs of a human being. So if you look here at this drawing made by Carlo Urbino di Crema that we find in the Codex Huygens from 1570, you see the correspondence between the various positions of the human body and here the epicyclic curves that you have on this drawing. What you have to understand it is that most probably Dürer, even if he's not mentioning that, is aware that this instrument was used at his time in order to simulate the movement of the planets. Because actually already the word planeo in Greek means to wander, to rover, because the planets, as opposed to the star, do not follow a circular trajectory regularly because they sometimes come back and then resume their course in their normal direction due to the relative speed of the Earth compared to the speed of the various planets. So this is an apparent movement, but this is the movement that the people were seeing at that time. And so they were using this type of instrument in order to explain all of this. So in the Renaissance, the same principles are applied to the movements of both the human body and the celestial bodies. Does this same principle of motion necessarily leads to a conception of harmony between the microcosm and the macrocosm? I'm rather doubtful. If we come back to the drawings of Carlo Urbino di Crema, obviously those drawings come from this very well-known drawing of Leonardo da Vinci, who was Carlo Urbino's master. And let us look much closely at this drawing, because in this drawing, which is most often described as the image of the perfection in Renaissance, I think that nothing coincides. Okay, just look, it is not that the square is inscribed within the circle as people would have it. It is that not only it is not inscribed, but look here, there is, it is wider by a small distance, and here it is wider by a big distance, and there is no obvious relation between those two distances. Anyway, Leonardo made this drawing as a montage between two successive sentences of Vitruvius' De Architectura, because Vitruvius says in the De Architectura, there is the body lying on the ground is inscribed within a circle, the center of which is the umbilicus. So first sentence. And then comes a second sentence where he says, the body standing up, erectus, is inscribed in a square, the center of which is, he doesn't say it, but you can draw the drawing and you see that it is the sex. Okay? But Vitruvius never says that those two drawings have to be put one on top of the other. This is an invention from Leonardo da Vinci. It is a montage intended to show, I think, that those drawings are not coinciding. And I think Leonardo da Vinci's contribution is to show that ideal schemes are not fitting with natural bodies. You know, whatever the will you want to establish and to find wonderful, ideal perfection, it is not fitting. And is this new? Not at all. Read, for instance, a philosopher that is Varro, who wrote the De Lingua Latina precisely at the time of Vitruvius, and the De Lingua Latina is precisely mentioned by Vitruvius. So what does Varro say to us? He says that it goes with the world as it goes with the human body. In both, you have an appearance center and an effective center. So in the world, there is an apparent center, which is the important religious center that was Delphi for the region of antiquity. But the real center of the earth is down into the underground, which you cannot see. And that's the same with the human body. There is an apparent center, which is the umbilicus, and there is a real center, which is, I'm quoting Varro, what makes the difference between man and woman. A little bit later, Theon of Smyrna, in his very important treatise, Mathematical Knowledge Useful for Reading Plato, says that there are two centers in the world. There is one called geometric center, the Earth, and a hot dynamic center, which is the Sun. So this correspondence between the movement of the celestial bodies and of the human body not necessarily reconduct to a thinking of harmony. So now if we come back to Dürer, you have to understand that if Dürer writes a treatise about geometry, it is because he renounced to a bigger project, which was to write a De Pictura, like following Alberti. He renounced to it, and he decided to fraction it into smaller treatises, one of which being a treatise on fortification, which is precisely it's a treatise of architecture, and another one on human proportions. And precisely in the treatise on human proportions, Dürer categorically rejects the idea of one single system of proportions, and he makes difference between men and women, between adults and children, and between different types of temperament. And not only that, those 38 different types are only a beginning that will be put into variation either with optical device or with what we would call nowadays optical topological deformations that you can see here. And to be sure, that was only a first level of deformations, because the real deformations comes with the movement. So in order to have 3D movement of the human body, Dürer will use another device, which is this one, and who should generate what he calls the snake lines. Unfortunately, the only drawing that Dürer provides us with is the instrument. We do not see the snake lines, which actually was announced since the very beginning of the treaty in the first real figure of the treaty. So we have to draw it. Let's see how it looks like. So this is the instrument, and now let's have it move. There it is. But of course, this is only one of the many snake lines that you can get with this instrument. Because if you read the text of Dürer, this is what he says. In the following, I shall show how to construct an instrument that can be used to draw a variety of lines that I would call serpentine line. The rods shall be arranged in a manner that they can be advanced by degree and can be shortened or extended. The instrument should also be made with few or many dials or rods, according to the intended applications. And so I will not follow on, but the whole comment is about variation. So actually, the real translation of this instrument is not the movement that generates one single line, but it is the operation of substitution that we can do on this instrument, by which I will substitute this rod by another one in order now to see what could be another trajectory or another snake line. So I hope to start to convince you that in Dürer's book, everything is about variation. The question comes now, why Dürer refrains from showing the serpentine line that he announced right from since the beginning of his treatise. So there are several hypotheses. I just mentioned one for tonight because there are other ones that deals with witches and many interesting things. But the polite answer is perhaps a kind of rivalry with Michelangelo, and especially with this model of this statue that Michelangelo took as a model for many of his works afterwards, the statue of the Laocoon, which was rediscovered in 1506, so precisely just after Dürer left Italy in his second trip south of the Alps. So now, because Dürer is not showing us the snake line, we have to interrogate the few figures that he has provided us with, and especially the diagrams that he showed us. So what you have to understand is that just after the instruments comes another series of actually more than 12 diagrams that you can see here. So you should consider that those 4 lines that you find in each of the diagram are the 4 rods of the instrument generating the serpentine lines. And then in the posthumous edition, Dürer added another diagram, which is this one. And what is very interesting, it is that this diagram that he calls der Vergleicher, and there is no perfect word for that in English, so let's call it the comparator, if you wish. So this diagram, actually you find out in each of Dürer's 3 treatises. Especially, you find it into the Treaty of Fortifications. So this is the image of this Vergleicher that you see in the Treaties of Fortification. So let's see what it's all about. The purpose of the Treaties of Fortification is to explain how you can protect a rectangular bastion by a series of circular walls. So the first thing is that those walls can be tilted in a varying way according to points that Dürer builds on top of the fortification. Okay, so there are two of those points, and for each you can get a different inclination of the walls. But most important in these treaties is the way with which Dürer draw the circular walls. So let's see that here. Here you recognize the Vergleicher, and the starting point of Dürer is that he draws a first circular wall. He gives it a thickness that is here 18 units, and the maximum distance between the circular wall and the rectangular bastion is 90 millimeters. Okay, so he translates the 90 millimeter in the length of this stick here on the diagram, and the 18 millimeters is the first interval that is described here. So let us look how this works parametrically. I just double click on the thickness of the wall, and now I make it 22. So because this interval has to have its endpoint lying on these slanting lines, the inclination of the stick is varying. And now we'll have also the total length of these slanting lines vary, and you see that it takes a different angle. So let's let it like this. And now we have another version of the three circular walls that protect this rectangular bastion. Okay? So I think this is really parametric architecture. And to be sure, the drawing of, so this is the convergence of the slanting walls. And here we see the final result as it was drawn by Dürer. So now let us look at the other treatise, the one about human proportions. So the image of the Vergleicher is this one, and it is important. It is the second one into this treatise. And let's first let's understand what Dürer is saying about it. He says that the three sections here, it's written in German, French, but what it means, it is that the trunk, so this part of the body, is to the thigh, whereas the thigh is to the shin. Okay? And this is to work this way. So here is a representation of this. And what I would like you to understand, this is actually already a complex instrument, because you cannot find the correct position which will give you this endpoint on this line, this other endpoint on this second line, and this last endpoint on the horizontal line. You will not find with a ruler and compass construction. So actually you have to build it as an instrument and move it here until this point lies on the horizontal line. It is not very obvious, but as you can see here, the trajectory of the endpoint is following a curve, even though it has a slight curvature, and it is not at all a straight line, as you can see with the dotted line. Okay? So it is actually a complex instrument. You will see later that in the instruments attributed to Plato, there are simple constructions that you have the impression are just made out of straight lines that cannot be built with a ruler and a compass. So this is the diagram that is the first variant of the instrument generating the snake line. You have to understand that in this diagram there is what mathematicians in antiquity, but still in the Renaissance, called continuous proportion. So what is a continuous proportion? A continuous proportion is a series of fractions that are equal, in which you find at the numerator of a fraction the denominator of the previous fraction. Okay, so you have A on B equal B on C equal C on D, and so on. Okay, and when you have three such fractions, or what we should call two equality, you have what in antiquity is called a double proportional mean, and the two intermediate mean are B and C. So since Hippocrates of Chios in minus 430, it is demonstrated that a double proportional mean enables you to calculate the duplication of the cube. So what is a duplication of the cube? You take a cube that has a side equal to the unit length, and you want to calculate what should be the side of another cube that has a volume that is a double of the initial cube. And of course, for us, the answer is straightforward. That's cubical root of 2. So how do you calculate a cubical root at that time where you do not have a computer nor a small electronic device? You just build instruments, or you build interesting construction. But first we have to understand that all of those constructions cannot be built with the ruler and the compass. So those constructions belong to what is called superior geometry, as opposed to elementary geometry, which is a topic of Euclid's Element. So superior geometry, as the name tells us, is actually the advanced field of research in mathematics in antiquity. That means that people will constantly come back onto those constructions, and actually we have, for the duplication of the cube, 12 different solutions that have been found in antiquity. But this is not only a theoretical field of research, it is also a very practical problem, since you find it in architecture for the calculations of volumes, for instance, for fortifications, but also in order to build war machine. And actually, if you read Book 10 of the De Architectura, you will find here the description of catapults or ballista, or generally war machines, where at that time you were using strings like this. So those are strings made out of animal tendons or women's hairs. Through the springs you pass two wooden sticks, and then you pull the sticks by the strings, and this puts the springs into torsion in such a way that if you release the string, you get the energy of the spring, which projects your projectile. So if you read Vitruvius, there are two different formulas according to the type of projectile you want to throw on your enemy. So if you want to throw an arrow, the diameter of the springs, according to which all of the elements of the machine are proportional, just as in the Greek temple, all of the elements are proportional to a single module, which is the diameter of the column. So in the war machine, if you want to project an arrow, the diameter of the spring is to be 1/9 of the length of the arrow. And if you want to project a stone, the diameter is to be 1.1 multiplied by the cubical root of the weight of the stone you want to project. So there again, we have the problem of calculating cubical root. And Vitruvius does not provide us a formula, but he gives us a table of value because he says it would be too complex and too long to calculate it on the battlefield. But in book 9, just before book 10 on mechanics, Vitruvius mentions a solution to the cube duplication. So we have to look at those two solutions before we go to those of Dürer. The first one is totally astonishing by the geometrical intuition it requires. So let's suppose you want to calculate the cubical root of the diameter of this circle, while this chord is the unit. What do? The first thing, you build a torus. Okay? And then you build a cone. The torus has here as a diameter, the diameter of the length you want to find the cubical root of. And here, the diameter is the axis of this cone that is generated along the segment that is a unit. And of course, those two shapes have an intersection curve, which of course is not planar. So now you build a third solid, which is this cylinder, and this cylinder intersects the curve into a point that is this one. And the 3 points that are this one, and this one, so you all know that 3 points in space determine a plane. So these determine the plane onto which you can build this planar construction, where this segment is the answer to the cube duplication. So it is really an astonishing construction, but it is totally inefficient on the battlefield. Okay? Because if you imagine that at that time you have no milling machine, so you have to sculpt marble or wooden torus, and then a wooden cylinder, and then a wooden cone, and look at the intersection, and be sure not to be accurate enough. I'm sure you won't throw any stone on your enemy. Okay, so you have to, well, Archytas was invented that we can estimate in minus 380 in Sicily. And each time Plato would go to Sicily, he would never miss to make a stop in Taranto to visit Archytas, who was not only a philosopher, a mathematician, but also a general in this town. So it occurred only 2 times. People kept on thinking on this problem, and the other solution that we know of via Vitruvius is this one by Eratosthenes. And I have first to convince you that it can be built mechanically. So if you would go to Modena in Italy, you would see this mechanical reconstitution that we can have work on our computer. So the idea here is to calculate the cubical root of this vertical segment, while this one is the unit. And for that, you pull a string between D and A, and then you move those elements in such a way that those 2 points lie on the same string. So Eratosthenes, who was living in Alexandria, was very proud of his device. You know, he wrote a letter to King Ptolemy and convinced him that if you use this machine, this computer, this wooden computer, you can build efficient war machines. You know, since antiquity, it's the same game. Scientists have to invent military purposes for their peaceful researches. So those are the 2 solutions provided by Vitruvius, and I have to convince you that Eratosthenes' device is very close to the one that Descartes would use into his geometry written in 1639, and who is precisely the start of what we call now analytical geometry. Even if Descartes advertises his geometry as being something new in order to solve the problem that the ancients were not able to solve, actually he is responding to their problems. And I think it is very important for us to understand that in science, you never build by just forgetting the past. You build by generalizing problems of the past. And I think that the avant-garde strategy that the modern movement used, you know, pretending, for instance, to invent a new modern architecture because there is now a non-Euclidean geometry, this is not at all corresponding to the way science is proceeding, since, as I told you before, precisely one of the models of non-Euclidean geometry was stereographic projection that was invented in antiquity. So let's look at the solution that Dürer is providing us and that he attributes to Plato. Yes? That's the last solution I will explain. So the principle of it is quite simple. Let's look at it. Here you see a very simple geometric diagram where you have actually 3 triangles that obviously are similar triangles. So that means that BE on DE is equal to BD on DC and equal to BC on CG. So that means that we actually build this, which is a continuous proportion. So if this is as simple than to build this, why all the fuss about this cube duplication? It is that actually it is very difficult when you start building this geometrical figure. As soon as you start from E towards D, there is only one perpendicular that leads to C and only one that leads to G. So you do not know what should be the angle, the starting angle here, in order that here this line arrives perfectly on G. Okay? So to do that, you have actually to build an instrument that is this one here, and I have to show you what can be this instrument, both in the drawing that Dürer provides us with. So that's the instrument alongside the geometric scheme that I did. And this is how it works if you build it on a software. So as you can see, if you take here as a reference this middle point here of this ruler, you can see that you have a varying spacing between this ruler here and this arm of the square, because here you have slot and pin joints, as the students know quite well now after the workshop. So to be sure, Plato did not invent this instrument. So this is a false attribution that actually Dürer is not responsible for, but that was made by Vitruvius at the end of antiquity. Vitruvius was studying geometry together with the architect who built Hagia Sophia in Istanbul. So they are the one who falsely attributed this instrument to Plato. But what is interesting, it is that this proves that already in antiquity, there were readings of Plato that were compatible with Plato building a material instrument in order to make those calculations. Okay? So there were materialistic and instrumental or mechanical reading of Plato already at that time. And this is of no surprise, because if you read the Timaeus, Plato explicitly says that you cannot understand the movement of the planets if you do not have under the eyes such an instrument that I will have move here. Okay, that draws very complex curves, and that was actually invented by Eudoxus, a brilliant mathematician at the time of Plato. So my conclusion is that the classical is not necessarily classic. That means invariable, symmetrical, ideal, abstract, and harmonic. More precisely, there are a plurality of traditions already in antiquity, and the tradition Vitruvius and Dürer belong to puts the emphasis on parametric and mechanical variations. To be sure, Andronikos' Towers of the Wind was already an information machine. Vitruvius' ballista was a war machine, the main parameter of which depended upon a complex mathematical formula with a cubical root, which in its turn was to be calculated with a mechanical instrument. So it's a calculus instrument that enabled to build a war machine. And temples themselves were the result of a complex parametric conception due to optical correction, well, at least in the De Architectura. Hence, parametric design is not new. Mechanics were an essential part of architecture since antiquity. And it is precisely on those grounds, parametric design and numerical command machines, that we can think of inscribing contemporary architecture within this other classical tradition. Thank you.
Academics, they're part of the Strong Research Environments. But before we do that, just if there's some quick questions to Bernard now. Otherwise, we will also continue the discussion with Bernard in the panel. Any quick question? 2 minutes.
Well, last night, it was fantastic. Thank you for an absolutely extraordinary lecture. This is my only question. But last night I was talking to you about Domenico Fontana, who moved to Obelisk, and asking the question why, in the Renaissance, according to how I looked, this whole mechanical tradition had kind of disappeared. So now you've answered me, of course it hadn't. But is there anything to say about why the Dürer and Italy, in the sense that you don't recognise any of this in the, or I didn't recognise any of this tradition in the canonical Italian treatises that we kind of say are the body of architectural, the architectural treatises that develops. If you take a kind of slightly naive view and you say, well, you have Plato, and you have Sally, and you have and this seems to be absent. I mean, is there anything very quickly to be said about that, or is it just too complex?
Well, there are in the room people that are much more competent than me on Italian Renaissance, but there's only one that I have had to study very carefully, which is Luca Pacioli. And I think that, to be sure, Dürer knew of Luca Pacioli's text, essentially the De Divina Proportio, and the Divina Proportio is divine because it is one single, invariable, incommensurable, which he calls irrational. And so this is totally the opposite of Dürer's mind. So for some reason, I think it's important to be very, very careful about the influences. So for instance, people associate Leonardo da Vinci to Luca Pacioli just by the fact that Leonardo da Vinci drew the wonderful perspectival image of the polyhedron at the end of Luca Pacioli's treatise. And they were in the same time, they were in Milan for a couple of years at the end of the 15th century. But you know, it's not because two persons collaborate that they think the same thing. So I think that actually Dürer, since his famous engraving, the one about Melancholia, made every effort to diverge from Luca Pacioli because he's not at all convinced of one single system of proportion. And this starts with the visit of Jacopo de Barbari in Nuremberg in precisely 1500, where Barbari explains Dürer that there are different proportions for the man and the woman. And so Dürer, rather than relying on two systems of proportions, will multiply that and make 38 proportions. So he goes very much into variations, which does not explain why the Italian will not follow this path of variation. We already talk a bit about it. I think there is a kind of effect of Alberti, who actually covered several topics of Vitruvius De Architectura. So you could consider that books 7 of De Architectura correspond to the De Pictura. You could consider roughly, it's not exactly, I mean, roughly speaking, it could be the way that it has been read afterwards. So if, to the extent that the De Pictura correspond to book 7 about the history of mural paintings, to the extent that the De Re Aedificatoria correspond to book 3 to book 6, okay? So then Alberti didn't wrote De Mechanica, but he wrote De Ludi Mathematici, where you have hints about mechanics. You have at least, if I remember well, there are levers, or there are hints at this type of problems, but it's still called Ludi Mathematici, which means mathematical games, okay? So it might be because of, you know, Alberti shaping, I think, in a way, the Italian theoretical landscape. It might be that people then say that, well, what is important in Vitruvius is what Alberti has taken in the De Re Aedificatoria. I think it's only one of the reasons. Because, for instance, Brunelleschi is known to have been a lot of machines, and probably the most interesting thing he did in the Duomo of Firenze are the machines used to build the Duomo. But just like in antiquity, the machines have disappeared. We are left with the churches and the temples, and the wooden machine disappeared.
Yes, Staffan.
Yes, thank you very much. It was fantastic, fantastic presentation. Also fantastic to see this representation of philosophical thought as you have done. I have a question where I am ending with asking for some speculation on the effects and implications of this. As you said in the beginning, that we're about to bring mechanics into the arts, and which in the part I feel this would mean a unification of technique and technology, which is obviously a fundamental, if not ontological, but ideological regrounding to how we understand art. But what does this mean? What will be the consequences of this? And I mean, how are we to understand this? How are we to proceed with this knowledge?
I think we should follow up on Tim's question, who was how all of a sudden mechanics disappeared from architecture. But I would be tempted to say how all of a sudden mechanics disappeared from art. Because if you read treatises of aesthetics since the very first we know of in Greece, so the treatise on the canon, it was all about mathematics. And I think that something happened very damaging at the time of Newton. I think by that time, you know, there is a huge bifurcation, which is if on one side Newton invents differential calculus, well, together with Leibniz. I don't know if there are Germans. So differential calculus appears, and the artists are not able to follow. Okay, but at the same time, you have Hogarth and Edmund Burke, who wrote a book about the serpentine line precisely, and who says that the principle of the serpentine line it is that it has no proportions, and that proportion is not anymore a discourse that is relevant in art. And they take precisely advantage of the fact that Newton has invented new mathematics to say, well, proportions are outdated. Okay, looks at Newton, he's making totally new mathematics. But just open the Principia of Newton and read the first proposition. It is a Greek proposition. So there is a total misunderstanding of the world of art about what is happening in mathematics. And I think the very first avant-garde is the one of Hogarth and Burke, okay, who thinks to invent something new, whereas actually they are not understanding what is happening. Just as the modern architect thought, you know, of using non-Euclidean geometry just to build cube, okay? And nowadays, with the digital avant-garde, again, we are living in a non-Euclidean world. Okay, so avant-garde is repeating itself since already a long time. And I think this is very damaging because since the time, we could say, of Newton, but probably also a start of the bifurcation started at the time of Desargues with the invention of projective geometry. Because, you know, there has been a very tough conflict in Paris between the artists who were willing to follow Desargues like Abraham Boss and the other one who said, well, no, you know, the rendering of distant objects should be done with color and gray nuances and all of these things. So I think it's between Desargues and between Newton that suddenly mathematics disappeared from art. And so then came up, you know, a full subjectivity, which paved the way for symbolism, for romanticism, and all of these things. And now I think we have to take the digital tool as an opportunity to re-establish the link between arts and science and mathematics in particular, but not on the basis of a new thing or an avant-garde, but on coming back to a state of the relation between those two disciplines that there were before.
We can take one more question. Okay. There is another in line, but do you want to reply short, Staffan? No, go ahead, Staffan, do that.
No, of course, so you mean that just as the neo-avant-garde repeated the mistakes of the historical avant-garde, the neo-avant-garde will repeat the mistakes of the prehistorical avant-garde instead. No, but I'm just kidding. No, okay, so it's a little bit but still, what is the ontological? I mean, in a sense, this is also a proposition of an understanding of the world. It's partly ideological, but partly also, I mean, it's an ontological proposition here. I'm thinking, I mean, due to the themes that you are addressing, one would think of Badiou perhaps, or Cretu in this kind of very mathematical conception of being. With some, I mean, so how would this in a more general sense, not just within the discipline of architecture, but rather in a historical sense? How will this inform us today in our understanding of being? Or, I mean, in a sense, it says quite a might have some thorough implications.
Yes, I don't know to what extent we should dive into philosophy, but I think that to be sure, Plato is a philosopher to be reread. The problem is that people only read carefully the beginning of Plato, whereas Plato, as I constantly repeat, has written for 50 years. Okay, so either you are stupid and you repeat the same thing for 50 years, or you or you change your mind. And Plato has to be read historically. I mean, so one of the reasons why I am deep into history is that everything bears a date. And each of the dialogue of Plato has a date, and there is a period that interests me most. It is the one where Plato has written The Sophist, where the artist is entitled to deform the optical deformation in order to simulate the real proportions. Okay, so I don't know if you understand the whole bunch of deformations in order to get to some kind of truth. And precisely the whole purpose of the sophist is to affirm a certain being of things like illusions, reflections, lies, and art. Okay? So to say that if those things were non-beings, how could we blame the sophist? Because we would blame him for nothing. Whereas we have to blame him for something. So there is something that exists and which is lie and which is illusion and all of these things. This is really modern, you know. I think nobody has gone down to that, you know. He's speaking of affirming the power of things like hairs or pebbles or things like this, you know. Reread the sophist. Even Nietzsche has not gone that far, I think. And then take the statesman. So in the statesman, Plato tells us that the paradigm of the paradigm is not the sphere of the potter, but is the interlacing of the weaver. But be very careful. in Greece at that time, there are only a certain category of people who weaves. They are women. So the paradigm of the paradigm is the specific activity of the women in Greek society. Already, you know, just those 2 points are just incredible.
Okay. We have one last question and then we go to the panel, but it's, what's your name?
Andre.
What?
Andre.
Andre.
Just a very brief question regarding this point of the relation between the new and the old. Can everyone hear me? Good. So on the one hand, we have sort of the avant-garde mentality, saying, oh, everything is ever new. And I can definitely see how your take on the problem would be a useful corrective to that attitude. So instead of saying everything is always new, you essentially say nothing is ever new. Go back to Plato.
I will not say.
Okay, I'm
sorry.
I'm simplifying a bit
Yes.
for rhetorical reasons. Because my question would be, isn't it also important to pose the third sort of in-between question? In the present situation, there might be nothing which is absolutely new, but what is relatively new about where we are today?
No, but precisely my discourse is to find a middle path. And during the workshop, I have clearly indicated to the students where something new happened. So for instance, perspective is something that is totally new in Renaissance. Okay, the intersection of the visual pyramid, we have no evidence of this having existed before. And so then this is only one first layer in what we call perspective, because then happens the projective geometry, where first there is the invention of the vanishing point, and then of the projective invariant with the involution and the biratio of Desargues. So, of course, there are new things. But most of the time, those new things answer to ancient problems. And I think the mathematicians are partly responsible for that, because, of course, if you read the beginning of Descartes' geometry, he starts blaming the ancients, whereas he's just rebuilding a more sophisticated mesolabium of Eratosthenes. Okay? So there are political and, let's be very honest, commercial strategy. You know, how you advertise yourself. Well, you say, I have invented something new, and everything that do my competitors is just outdated. Okay? So now the problem is that if you are selling just a commodity or a product, there is not too much of a consequence about that. But in a city, which is a sedimentation of historical traditions, then it starts creating a problem. You know, for instance, when Le Corbusier shows images of Paris reduced to a series of towers between which you have airplanes that circulate, I think this is very, very, very dangerous.